Hey everyone, if you're gearing up for that big calculus exam and trying to master the critical rules of differentiation, you are in exactly the right place. Today, in this explainer, we're unpacking the core concepts from video 13 of your Mathematicae series. We're going to cut through the noise and focus strictly on what you need to know. The derivative is, at its absolute heart, simply the rate of change at a single instant. It's the exact slope of the tangent line, not the secant line, and it literally shows up everywhere in engineering, from calculating velocity to analyzing stress gradients in materials. So grab your notes, get focused, and let's conquer these rules together.
Here is our quick roadmap for today. 1. The instantaneous rate. 2. Secants, tangents, and limits. 3. Product and chain rules. 4. An exam walkthrough for nested functions. And 5. An engineering applications recap. Let's get right to it.
All right, part 1, the instantaneous rate.
Before we get completely lost in equations and formulas, we really need to establish the physical intuition here. If you can visualize what the math is actually trying to do, the formulas become so much easier to remember. So, I want to pose this fundamental question to you. How do we measure change at an exact instant? Think about it for a second. Calculating an average rate over time? That's simple. If you drive 100 miles in 2 hours, your average velocity is 50 miles per hour. But what if I ask you for your exact speed at precisely minute 32 of your trip? That is the true challenge of calculus right there. We are trying to pinpoint a specific, frozen moment in a continuously changing system.
Check out this graph. That blue curve, let's say that represents a moving body's position over time. The red dotted line connecting those 2 points is our secant line, which gives us the average velocity over that specific interval. But to find the exact speed at a single point, the instantaneous velocity, we have to shrink that time interval down until those 2 dots literally merge. And when they do, that secant line transforms into the tangent line, touching the curve at exactly 1 point. The slope of that tangent line, that is your derivative.
Moving right along to part 2, secants, tangents, and limits. Okay, so now that we have the physical picture of a secant shrinking into a tangent, we need to translate this into the formal mathematical notation you'll definitely be tested on. The crucial concept here is contrasting the difference quotient with the actual derivative. The difference quotient is exactly what we just looked at, the slope of the secant line. It's written as f of x minus f of x0 divided by x minus x0. It's just good old change in y over change in x. But how do we get the tangent? We apply a limit. The exact derivative, f prime of x0, is the limit of that difference quotient as x approaches x0. We literally shrink the distance between our two x values to 0. That limit is the mathematical engine giving us our exact instantaneous rate of change.
Which brings us to part 3, product and chain rules. Listen, calculating limits from scratch every single time you need a derivative on an exam? No way. That would take forever. Thankfully, we have patterns. Consider this your mental checklist, your differentiation toolkit. First up is linearity. If you have a constant times a function, or you're adding functions together, you just take their derivatives individually. Super easy. Then we've got the quotient rule for fractions. But the absolute heavy hitters you must memorize for your engineering math exams are the product rule and the chain rule. The product rule tells us the derivative of two multiplied functions, f times g, is f times g prime plus f prime times g. And the chain rule? That's for nested functions, a function inside another function. The derivative is the outer function's derivative, with the inner function left alone, all multiplied by the derivative of that inner function.
Let's see this in action in part 4, exam walkthrough for nested functions. Knowing the rules is great, but applying them under time pressure is a whole different ballgame. Let's look at the product rule first. Say we're asked to differentiate x squared multiplied by the natural log of x. Our first function, f, is x squared. Our second function, g, is ln of x. Notice how we differentiate them completely separately first. The derivative of x squared is 2x. The derivative of ln of x is 1 over x. Now, we follow our formula and cross-multiply. The first function times the derivative of the second gives us x squared times 1 over x. Then we add the derivative of the first times the second, which is 2x times ln of x. Simplify x squared times 1 over x to just x, and your final answer is right there. X plus 2x times ln of x. Boom, full marks.
Now let's tackle the chain rule and see how it works with nested functions. We need to find the derivative of e to the power of x squared. This is literally a function trapped inside another function. We treat the exponential, e to the power of y, as the outer function, and we treat x squared as the inner function. Remember our rule? Differentiate the outside,
Leave the inside alone, then multiply by the derivative of the inside. Well, the derivative of e to the power of anything is just e to the power of that same thing. So the outer part is simply e to the power of x squared. Now we multiply that by the derivative of the inner function. The derivative of x squared is 2x. Multiply them together, and you get e to the power of x squared times 2x. Simple, right?
To make sure you don't panic when you encounter complex or nested functions on test day, always follow these 4 steps. Step 1. Identify the rule you need. Is it a product, a quotient, or are functions nested? Step 2. Break the equation into clear f of x and g of x components. Step 3. Differentiate those parts individually on the side of your paper. Seriously, don't try to do it all in your head. And step 4. Combine them using the correct formula. If you stick to this structure, you're way less likely to drop a negative sign or forget a term.
Finally, Part 5, Engineering Applications Recap. We've done the heavy lifting with the math, so let's tie it all together. Here is your ultimate decision matrix for the exam. The most common mistake students make is confusing when to use which rule. You've got to cleanly separate them in your mind. If you're multiplying 2 distinct separate functions, like x squared times sine of x, you absolutely use the product rule. But if you have a function stuffed inside another function, like sine of x squared, you must use the chain rule. Knowing the difference just by looking at the equation is half the battle.
And hey, why does this actually matter for engineers? Because setting a derivative to 0 to find a peak or a valley isn't just a math puzzle. It's how you're going to find the maximum stress point on a steel beam, optimize a motor's efficiency, and calculate exact rates of change in physical quantities like fluid velocity.
I want to leave you with this really provocative thought straight from your materials. The derivative provides the best linear approximation of the function in the vicinity of the point x0. Think about that. When a physical system is too complex, too curved, or just too messy to calculate precisely, engineers use the derivative, that tangent line, to create a simple, clean, linear approximation exactly where it matters most. It is your ultimate tool for taming the chaotic curves of the real world. Keep that in mind as you practice these rules. Apply that step-by-step method, and you are going to completely crush this exam.